exactly zero angular momentum. So in a sense, what we see here are different Lagrangian regions, so areas in the initial conditions from which halos will form, integrated, where their angular momentum is integrated from the center of mass. And we see these kind of empty spheres, zero angular momentum spheres. And so in a sense, the full angular momentum of the protohalo is included in the region that is outside of this largest enclosing, largest contained sphere. Also, this means that internal rotation is not coherent, which touches on your point, because indeed we cannot think about a protohalo as being some ellipsoid that is being coherently rotated by the tidal field, because indeed within this sphere there is actually zero angular momentum. Let's go into this a little bit in more detail, this incoherent internal rotation. So what we see here is a two-dimensional cosmological simulation. We see the initial and final state, and this is the movie that shows the evolution, where we, on the right side, we see a Eulerian picture, so we see as structure collapses over time. On the left, we see the Lagrangian picture, meaning each particle here is kept at its initial position. What the color shows is the angular momentum of each particle. So what we see in the initial conditions, and essentially blue and red gives you inside and outside of the sphere. So this is again a two-dimensional cosmological simulation. What we see is that the angular momentum distribution within the halo actually has this quadruple pattern. So things rotate in opposite direction within the halo. What happens over cosmic time is that there is mixing between particles that start in different places, and we see that in the final situation, the angular momentum magnitude here is scaled appropriately with cosmic time. We see there's a lot of mixing, and the typical angular momentum value within the halo is more like white, is more like close to zero. So we have large angular momentum values locally that in the end mix together.
Sorry?
Now this.
Sorry, I missed the point here. The proto-halo is defined in the initial conditions. You will take a final halo and the particles
Right,
make
exactly.
the final halo.
Right. Yeah. So this is a two-dimensional cosmological simulation. Let's just look at an example of what this looks like in a three-dimensional cosmological simulation. This is the same as here, essentially red and blue shows you so the color shows you the component of the angular momentum that's parallel to the overall integrated angular momentum of the halo. Red and blue show angular momentum pointing in positive and negative directions, and you can see maybe there's some trace if you squint of this kind of quadruple signature that you see clearly in the 2D case, but clearly it's very complicated and different parts of the halo rotate in different ways. Okay, excuse me. So let's go through a few important characteristics of the angular momentum of halos at the final time. So early on, Peebles defined this parameter that we call the spin parameter. It essentially shows the fraction of support of the halo that comes from rotation versus internal random motions. This is found in simulations to be roughly universal at a value of about 3%, only 3%. It has a log normal distribution, it's roughly independent of mass and also independent of redshift. Since it scales like the angular momentum divided by, so it's the specific angular momentum divided by the typical velocity and the typical radius of the halo, this means that it scales roughly as the mass of the halo to the power of 2/3. Now this reminds us of the observations from the first slide, where the same is true for the specific angular momentum of galaxies, of stellar components. So if one connects these two things together, this gives a very interesting clue. So essentially, if one assumes some empirical model for a connection between the stellar mass and the halo mass, one is able to put on such a plot lines that show a fixed value of the lambda parameter, essentially, or of specific angular momentum. And this blue line that goes roughly through disk galaxies tell you that the specific angular momentum of the stars is almost equal to the specific angular momentum of the halo, while this red line shows a significant, if you want, call it loss of angular momentum. The specific, elliptical galaxies have specific angular momentum, but it's 7 times lower than what their halos, the specific angular momentum of their halos are expected to Also, there is a universal angular momentum profile within halos, where specific angular momentum scales roughly as the radius. This is, you might expect this from an isothermal sphere approximation to halos. And also the angular momentum direction within halos is not completely coherent, so there is some twisting of the direction of the angular momentum. So between the inner parts of halos and the outer parts of halos, there's some angle, relative angle to the angular momentum. Okay, so these are the basic properties that I chose to show about the tidal torque theory. Let's see how it compares to reality, so simulations, of dark matter-only simulations. So in the simple picture, you would expect the direction of angular momentum to stay constant over time, right? So there is nothing in this expression that I showed earlier that the direction is essentially determined by the interplay between the moment of inertia, initial moment of inertia, and the tidal tensor, and then grows until it stops. In reality, what we find in simulation is this is the distribution of the angles between the angular momentum in the initial time, in the linear phase, and the final angular momentum of the halo. This would be a random distribution. This is the actual distribution measured. So it's certainly not random, but it's also not delta function at zero. So there is significant reorientation of the angular momentum over cosmic time. And this shows this angle as a function of cosmic time. You see most of this reorientation occurs at maybe, let's say, redshift 2 or so, so roughly at the turnaround time of halos. So most of this reorientation occurs in the non-linear phase, which the simple theory assumes in which angular momentum is conserved. Also for the modulus of the angular momentum, the theory predicts the average spin parameter very well, but actually it does quite terribly on the halo-by-halo individual basis. So this shows the distributions of the ratio between the expectation of the model and the actual angular momentum simulations. It's distributed around 1, but with a scatter of order unity as well. Okay, so we'd like to try to understand where these deviations come from, but also I want to add in the baryons because I've only talked about dark matter so far. So for determining the baryonic or stellar angular momentum, one has to make further assumptions. So one assumes that the baryons of dark matter obtain the same angular momentum, in specific angular momentum during the linear phase, and then that once the angular momentum stops and being conserved for the dark matter, as baryons collapse to the centers of halos, they also keep their angular momentum that they gained in the linear phase. So these are the basic assumptions for the simple theories of this formation. The implication of this, you can infer from this that there would be a relation between disk galaxy size and halo size, and the proportionality between them is essentially the spin parameter. This is...
sorry, we go back to the angular momentum definition that was actually second derivative of gravitational potential.
Mm-hmm.
Does that mean that you assume baryon and dark matter to have the same gravitational potential, or can you just say because it's additive, right?
So we assume they are distributing in the initial condition identically, and they see the same gravitational potential.
Okay, but over the time it will change, so you should see
Right.
some anomalies between baryons and
Yeah.
dark.
So I'll touch on that. Yeah, it's an
Okay.
important point actually.
Right.
Okay, so we actually see in empirical models, so essentially there's empirical evidence that we see here for this ratio, galaxy size over spin parameter times halo size, to be constant over cosmic time and mass. So this seems to, these assumptions seem to work. They're also reproduced by certain simulations. So for example, in green here, the elasticity in G, and in black, these empirical constraints. And so they're reproduced by hydrodynamical simulations. On the other hand, if you look in a bit more detail on a one-to-one correspondence, this shows this ratio, disk to halo size, versus the spin parameter. Again, from this simulation that reproduces the overall constancy, there's almost no correlation. So again, it doesn't work on a case-by-case basis. Another implication of these assumptions is that essentially they can hold only for these galaxies, but ellipticals must be the result of a significant angular momentum loss. As we've seen, they have much less specific angular momentum. So I want to now go a bit deeper and examine these assumptions more carefully in cosmological hydrodynamic simulations. So what's shown here is that the current empirical evidence shows that these galaxies have only have lost maybe 20% of their initial angular momentum according to these assumptions. In the past, this estimate was more like about half. So a simple model that came out a few years ago said the following: maybe we don't have to assume that the baryons actually lose angular momentum to end up with galaxies that have lower angular momentum. Maybe the stellar part of galaxies is actually formed just from the inner part of the halo. And the inner parts of the halo have lower angular momentum, as we've seen. So essentially they said, okay, they asked what radius within the halo do we have to assume that the baryons came from so that we get lower angular momentum for the stars than for the halo as a whole. And they found this has to be about 60% of the virial radius. They said, maybe you don't have to consider loss, but just that the baryons come from the inner part of the halo. What we can test this in simulations, and we find somewhat of a similar picture. So what's shown here is the modulus of the angular momentum of the stars in a galaxy versus the modulus of the dark matter angular momentum, but in the initial conditions, so not at the final time. So essentially I take all the stars and all the dark matter at redshift 0, I follow them back to the initial conditions of the simulation. So it's called it's the angular